This is my final project for controls. For this project, I will be designing a heating system for a car. Here is the physical problem that I'm trying to model. The system is the heating system of a car that delivers a hot air to the cabin. Now, the way this usually works is that a coolant gets heated up by the engine, which then is taken up to the heater core, which then heats up air around the heater core, and that air gets pushed into the cabin via a fan. Now, for this, I will be simulating a car during the winter, which means that the coolant temperature will be at 0, and we wanted to have it go up to a steady state, which will be determined by the user input. Now, to mark this a success, I will have to have a steady state error less than 1%, a response time under 5 seconds, and I will also have to develop a control that minimizes the overshoot. Now, modeling this system isn't as simple, but I had to make a lot of assumptions and simplify the system a lot. Some of the assumptions I made was the coolant started at 0 degrees Celsius, and the coolant, in order to minimize the work I had to put into researching all these properties, I just assume all the properties of water are the same as the coolant. Since the coolant is at 0 degrees Celsius, I have to assume that it's not frozen, that it's just barely at that close to that 0 degree temperature. Now, like in a real system, the engine would constantly keep adding energy to the system, and that's what's assumed in this system. Now, since the heater core also has a fan behind it, which varies the speed of it, and before it even gets to the cabin, the vent has to be fully open or close to open. For this system, I assume that the fan is at 100% speed and the vent is all the way open. Now, the sensors that I'm going to be using for this is just one temperature sensor, which reads the output temperature from the heater core, and eventually that's what's going to get feed back into the system. Now, the control that I chose to model here is a proportional integral derivative controller. A PID basically takes the input error and then modifies it so that once it passes the progress, it has the minimized error. Now, the temperature that the sensor is acquiring is the temperature that's going to get fed back into the system, and then that error is what is going to get minimized by the PID. Here is a model of how I chose to simplify this system. As you can see here, the age would be just the engine adding energy to the system. Theta I is the input temperature of the coolant. Theta O would just be the output temperature of the heater core. Now here to my left, we can see a derivation of the system, and here equation 1, we can see an equation that models the output temperature in response to the energy and the input temperature added to the system. Equation 2 is just taking the Laplace of equation 1 and making it so that it's a transfer function that is based on the input temperature and the energy added to the system, which we can see down here in equation 2. Now, in order to get the thermal resistance of the coolant, we have to take the inverse of the thermal conductivity of this. Now, this property was taken from water at 20 degrees Celsius, and here we can see the resistance calculated. Now, for thermal capacitance of this coolant, it's a function of it's just a simple formula from the volume, the thermal capacity of the coolant, and the density of this liquid. Now, for this volume, I assume just 1 meter square as a rough estimate of the engine, the volume of the engine that comes in contact with the coolant. And here we can see the capacitance calculated. Now, once I had this transfer function, I can input this into Simulink, put an input to it, and then that would give me a response, and that response is just the output temperature over time. Here we can see that the output temperature is very slow, and it's not a very responsive system. As you can see, it doesn't even go up 1 degree in a span of 20 seconds. This is not an ideal system, and we have to manually create. This is where we would implement a controller in order to get a faster response time. Now here we see a modified Simulink model that represents, on the top we see the simple transfer function, the raw data that we saw before. And under that we see a modified system that has some noise to it in order to simulate a more real world situation in which the temperature is not always as smooth as we want it to be. It's always going to be very independent of whether or not there's wind affecting the system, if there's any kind of losses of energy from the engine. And this noise is going to accommodate for that. Under this under this transfer function, the last transfer function under this, we can see that we incorporate a PID to the system in order to have the desired output. Now, after putting the PID into the system, it has to be tuned in order to have the correct response. Now, the way I tune this PID would be so that it would give me a fast response time, and the overshoot for this system doesn't really matter that much, just because when you're going into a car that's at 0 degrees Celsius, the ideal situation would be to have a temperature output that gets to 80 degrees as fast as possible. Now here we can see the graph. The yellow line, it represents the system model without the controller, and we can see that it's very slow. It doesn't even move above 0 after 20 seconds or 30 seconds. Under that, we see the blue line, which is the system with the noise. That's just the temperature oscillating. And the red line represents what the response is after we include the PID controller. Now for this PID controller, we see an overshoot of 18%, a steady state of 80 degrees Celsius, which is ideal, and a very fast response time of 2.5 seconds. Now this system is a very idealized system with a lot of assumptions and a lot of simplifications. So in the real world, the output would be not as smooth as what we have modeled, especially since the system depends on the fan speed and how wide the vent on the cabin is open. Now, in order to accommodate for this, we would have to test the PID with different fan speeds and different sizes of the vent. Now, this is something that has already been installed in most cars, and there's no ideal situation where a person would be able to do this. So it makes sense to automate something like this. This is ideal for cars in order to have the engine cool down as fast as possible.